So let's see. When it comes to hydrocarbons, we have mainly four paths, beta. One is alkanes, alkenes, alkynes, and alkadienes.
Hmm.
And alkanes, let's see, first part of it. Mainly, every time we study about a functional group, you would be emphasizing in two things. One, what are their physical characteristics? The other one is what are their chemical reactions. Now, when it comes to alkanes, C1 to C4 carbons generally are gases, C5 to C17 are liquids, and anything above C18 are waxy solids, petroleum
Okay.
jelly, right?
Yeah.
And those kind of waxes which are typically going to have carbon 18 and above. Got it? So this is
Yes.
a very important statement as well as the information which is asked directly in JEE mains exam. So you better remember it. C1 to C4 are gases, 5 to
Hmm.
17 are liquids, above 18 and above are solids. Next thing you would be asked is to describe about their boiling points. Alkanes are non-polar in nature. You understand this terminology? Non-polar means there is no dipole moment, resultant dipole moment it carries. The resultant dipole moment is zero. Since they are non-polar, usually their boiling point or melting point are low. Okay. Now, boiling point depends on two important factors. One, what is the molar mass of that particular alkane? Second, what type of interactive forces it is giving. Okay.
Right.
If usually you compare a hydrocarbon which has less molar mass compared to the higher molar mass, tend to have
Hmm.
lower boiling point. For example, if I compare methane with propane, usually I can say propane will have more boiling point than methane. Okay, without
Yes.
much thought into it, without much emphasis of what kind of forces we have, nothing. The first priority you would notice is molar mass. Okay. Now, second priority you would check out is intermolecular forces of attraction. Usually, for any boiling point purpose, I mean, for any compound, if they have more intermolecular forces, we say their boiling point is higher because boiling point
Yeah.
depends on how the molecules are attracted to each other because I need to separate them out and convert them into vapors.
Hmm.
So, more the force of attraction, more is the temperature required. Therefore,
Yes.
more interactive forces, more is the boiling point. Along with that, suppose if you usually have more surface area covered by the molecule, it tend to always possess more intermolecular forces. For example, if you have a pentane versus an isopentane here, this is called N-pentane, this is called isopentane. Got
Yeah.
it? Now, in this case, when you have N-pentane, because there is no molecule studied close to each other, usually it will spread over a larger surface area. While
Hmm.
if you have isopentane or neopentane, this is covering lesser area, this is covering even smaller area,
Hmm. The boiling point would
which
be
is
less.
what we call it as branching. So
Hmm.
higher the branching, less is the surface area occupied, and less the surface area, weaker are the interactions. Got it? Interactive forces typically depends on how much amount of surface area it is gathering. If it's occupying a smaller surface area, imagine this. If you have a larger surface area, positive and negative charge can be properly distributed. But if you
Yeah.
have very small area, you will not be able to distribute that positive negative charges easily.
Hmm.
Therefore, interactions becomes weaker if the surface area is smaller.
Okay. So if surface area is smaller, the intermolecular forces is less.
Mhm. True, correct.
Okay.
So
No, I was
which
just
eventually leading to lesser boiling
lesser
point.
boiling point.
Perfect.
Yes.
So you could notice here 5 carbons, 4 carbons, 3 carbons, 2 carbons. They typically depend on molar mass.
Hmm.
Second thing, if you have an isomeric hydrocarbons, which meant that they have same number of carbons. Now
Yeah.
this is N-pentane, isopentane, neopentane. So what's happening? More is the branching, lesser is the interactive forces, and lesser is the boiling point. While on the other hand, melting point depends on the symmetry of the molecule.
Hmm.
Melting point, when do we say something is a melting point? When we are trying to convert a solid to its respective liquid
Liquid.
state,
Yeah.
isn't it? So
Yeah.
if that solid is very strongly bonded, can I conversely say that possibly it might have a very healthy stacking of particles, or
Yeah.
what we call it as a very symmetrical stacking of particles? So if a
Okay.
symmetry is better, chances are in the unit volume you will have more number of particles stored,
Hmm.
correct? So
Right.
symmetry usually is found better in a even number of carbons compared to odd number of carbons.
Yeah, because it's easier to divide.
True, right? So that's why you would notice even number of carbons usually have a better symmetry than odd number of carbons. So if you are comparing the carbons which are very close by, for example, 6 versus 7, 8 versus 9, then typically 6 would be greater than 7, although 7 has more molar mass, 9 has more molar mass.
Hmm.
Got the point?
Yes, sir.
Right. But this does not extend to a very larger part. It will go maximum up to 10, and furthermore, it is only depending on molecular weight. Okay,
Okay.
because symmetry does make sense to a smaller particles. When
Hmm.
it becomes very larger particles, now anyway, it becomes very difficult to stack them in a unit volume because these are not linear particles, isn't it? All
Yeah.
these hydrocarbons have carbons which are sp3 hybridized. So they are
Hmm.
highly three-dimensionally stacked particles. So if the chain becomes larger, thereafter it does not depend on symmetry, it only depends on molar mass. So you
Yes,
would
sir.
see this, difference of symmetrical distribution only up to 10 carbons. After that, you will not see that logic.
Okay. But
Moreover, yes, Vijay.
for boiling point, it applies for everything. The number
See,
of carbons
boiling
doesn't
point,
matter.
listen, boiling point is already in a liquid state. So there is no point
Hmm.
of symmetry now. You are
Ah,
converting liquid to
yes.
gas, no, bacha? So here
Yes.
symmetry does not impact anything. All right. So there it is only molecular weight which is most important. Got it? Right.
Yes, sir.
Next point is experimentally, this is what has been noticed. Ethane is greater than methane, greater than propane. Because at a smaller scale, smaller carbons, the stacking would be much better if it is a, what do you say,
Yeah.
even carbons. Next,
Ah,
butane is better than isobutane, and neopentane is better than n-pentane, greater than isopentane. This is an exception. You just have to mug it up. There is no logic to it. This is an
okay.
experimental data. Clear?
Yes,
If
sir.
you ask me, as per NCRT, only these two data are given. So, as much JE mains is concerned, possibilities only this could be asked. Okay. Worst
Okay.
case, sometimes in JE advanced, very old papers of JE advanced, this was once asked. Okay, beta.
Hmm.
Not in recent times, not in last 15 years at least. Okay. Hmm.
Okay.
Let's see this. Another important factor of hydroalkanes is heat of combustion. See, what is heat of combustion? It is the amount of heat that is released when you burn a hydrocarbon with excess oxygen.
Yeah.
Definition is simple,
Yes, sir.
right? Now, heat of combustion, the first thing it depends on is how many number of carbons the hydrocarbon possess. More the number of carbons, more is the heat of combustion. Simple. Okay. In short, you think this way. You're breaking a carbon-carbon bond, then you're making a C double bond O, isn't
Yeah.
it? You're breaking one bond, but you're making two bonds with oxygen.
Hmm.
So in a way, you are making much stable bonds. So if you have more number of carbons, more C double bond O will form. More
Oh.
C double bond O forming is more energy is released.
Hmm.
So it is directly related that more the number of carbons we possess, more the heat of combustion. Secondly, it also depends on branching, but it should be isomeric. Just like boiling point case, how we learned earlier, it is a similar case now. If you have a more branching part here, isn't it?
Hmm.
Then again, the interactive forces are weaker. So interactive
Right.
forces are weaker. That makes it to have a lesser heat of combustion. Got it? So you would notice that straight chains would have more heat of combustion compared to branch chains. Got it? Any doubt here, beta? Right.
So
Now,
can you
on the
repeat
same
the
logic, hmm?
so can you repeat the part about branching?
Yeah, notice this. What I'm saying, when it comes to branches also, heat of combustion is about breaking the carbon-carbon bond and converting all of them into carbon dioxide,
Right.
isn't it? Okay.
Yes.
Now, if notice this one, this is how the molecule is. The next molecule is like this, correct? Now,
Hmm.
how the interactions here are irrelevant. But But what is important here is if you have a particle like this, let's say I'm breaking carbon-carbon bond here, carbon-carbon bond here,
Hmm.
carbon-carbon and carbon-carbon bond here. In case
Oh.
if you have something crowded here, for oxygen to enter here and break that carbon-hydrogen bond or coming here, if you compare oxygen coming here and oxygen coming here, it becomes challenging for oxygen to come here because of the
Yeah.
crowding of carbon. Okay.
Okay.
That's why
Understood.
for oxygen to enter that space itself is becoming challenging.
Hmm.
Okay. So in the
Yes.
branched form, it requires more energy for oxygen's movement to go and interact with carbon, break carbon hydrogen bond, then make a double bond, isn't it? So that's
Yeah.
why usually if you have more branching, it becomes difficult to make that carbon dioxide and make it to release more energy.
Okay, sir.
Make sense?
Yes, sir.
Right.
Understood.
Next one. I was telling you something about here. See, in case if the hydrocarbons are cyclic, okay, then how do we compare the heat of combustion? For example, if you have a three-membered ring, four-membered ring, five-membered ring, and a six-membered ring, if I have to compare heat of combustion, right? You know, any species which is unstable will be ready to release more amount of energy.
Hmm.
Okay.
Yeah.
Now, cyclopropane is highly unstable because of its huge angle strain.
Hmm.
Okay.
Yeah.
Here also there is an angle strain. This has the least angle strain. Despite that fact, the first factor what you need to check is number of carbons. Okay, beta? Which has more number
Okay.
of carbons?
This hexagon has more number of
See,
carbons, but
even though it is very much stable, it
yeah.
will still release more amount of heat of combustion because that's what is the first thing I told you. The first priority is check out number of carbons.
Okay.
So heat of combustion,
Yes.
first factor depends on number of
Number of
carbons. What if I give you something of a similar kind like this now? I have three methyl substituted. I have two methyl substituted. I have one methyl substituted. And now I have cyclohexane. If I have to compare these four now,
so
in
one
that
second, let me
case,
count.
hmm,
So all of them have the same number of carbons.
hmm, So now it is not the number of carbons anymore. It is the stability which you have to check now.
Oh, okay. So the first one will have the maximum heat of
Yes, the
combustion, and
first
then
one
so
will have
on.
no maximum. Correct.
Yes, sir.
This is very confusing but very important as well. Okay.
Okay, sir.
Asked multiple times in JE questions. Please remember that. Okay.
Yes, sir.
In the first case, it's always about number of carbons. In the second case,
Mm.
because the number of carbons are same, you will notice the stability.
Okay, sir.
Okay. Right.
Yes, sir.
Now, whenever it comes to chemical reactions, there are two things we will see for any functional group in organic chemistry. First, how it is prepared. Second, what are the chemical reactions it can make.
Mm.
Okay.
Yes, sir.
Here, specifically for alkanes, we will do the reactions first. That means what kind of a reactions they will be involved. And second, we will do preparation reactions. Okay, beta?
Okay.
So, the first type of reactions, alkanes are involved into radical mechanism. Okay. See,
Mm.
alkanes are typically one of the most stable compounds of hydrocarbons, isn't it?
Yeah.
For organic compounds, if you notice, alkanes are very stable. They are less likely to react anything directly with some reagents or acids or bases.
Mm.
Correct. But yet there will be some chemical reactions. And one of them, which is very standard reaction of alkanes, is radical reactions. Okay. The
Okay.
radical reactions, the first type of reaction is free radical substitution. Now,
Mm.
what does this mean? Let me show you first the overall reaction. Imagine if I take methane gas. Okay, this is something now you have to start developing the imagination. Okay, so start getting into that imagination world now. Imagine there is a methane gas.
Mm.
Okay, and you kept that methane gas in some kind of a tube or a container or something. Okay, then
Okay.
from one end the ethane gas is coming, from the other end the chlorine gas is coming.
Mm.
Okay, now you're exposing this entire setup into light. So imagine that entire tube is made up of glass that
Okay.
let the light to penetrate through it.
Mm.
Okay, so
Yes,
when
sir.
that light goes into it, methane and chlorine will start possibly breaking their bonds. And when they
Yeah.
start combining together, you might see this as the overall reaction where you would have methyl chloride forming and HCl vapors forming. Everything is in gas, by the way.
Yeah.
Okay,
Yes,
right.
sir.
This might be the overall reaction that might happen. So, are you clear with the imagination now? Now,
Yes,
let's
sir.
see how it might be happening. See, when the light is passed, when the light is passed,
Mm.
light would first break the chlorine bond, Cl-Cl bond. Now you might wonder, sir, why not carbon-hydrogen bond? Why not carbon-carbon bond? Why only chlorine-chlorine bond? Okay. Now,
Mm.
this is where there is a certain importance of property of light. Got it? See,
Okay.
light usually have both electronic wave, electrical wave, as well as magnetic wave. Got it?
Mm.
So every light is something called as electromagnetic radiation, EMR. Hmm?
Yes, sir.
So if that radiation is coming inside, it would always like to interact more with the electron cloud. Okay, and you notice that
Yeah.
the electron cloud density is more on chlorides as compared to carbons, because carbons does not have any lone pairs or something,
Mm.
isn't it?
Yes,
So
sir.
which one would have more ability to interact with the light? Chlorines. So chloride would definitely have more ability to interact with light first. So light,
Mm.
as it falls on chlorine, immediately chlorine will break into this kind of bonds. This is called homolytic fission. Fission is bond breaking. Okay,
Mm.
homolytic means it is breaking the bond, the covalent bond, into equal number of electrons. So
Right.
if one single line is made, which means there are two electrons, isn't it?
Two electrons. Yeah.
So now one electron has carried forward to this chloride, the other electron is carried to this chloride,
Mm.
and that way you will get now two Cl dots.
Okay.
So this dot represents radical. Okay. Now,
Yeah.
if you compare those radical forms, chlorine originally had 6 electrons, and the seventh electron is what went here, isn't it?
Right.
And this is how it has broken. So now the Cl has 7 electrons, isn't it?
Hmm.
Each chloride has 7 electrons.
Yeah.
Now, in the first place, chlorine originally also had a 7 electrons, right? In the valence
Yeah.
shell. The reason for it to bond is to get that octet,
Yeah. Stability.
isn't it? So to
Hmm.
gain that stability, to get that octet form, it was trying to make a bond. Now, when you break it again, it is incomplete octet. So it is again becoming highly unstable.
Hmm.
So usually radicals requires huge amount of energy, and light provides. See, if you heat also the reaction could happen.
Hmm.
But with light, the advantages that light energy is very concentrated energy focusing only on one bond. So that way, the amount of energy that is required to break that bond precisely happen to fall on that chlorides only. So it's not getting
Hmm.
waste, or it's not getting spillover or something. So therefore,
Okay.
this radical will be highly unstable, right?
Sir, I
Now,
have a question.
yes, beta,
So when we write just like a normal chlorine atom, we don't call
right?
that a chlorine radical, but once like Cl2 gets broken to chlorine
Mhm.
chlorine, we write that as radical. So like why is
Is
there a
the
difference
is
in
anywhere the chlorine exist? Cl dot, I mean, as a single atomic chloride exist?
no,
No, correct. Can you isolate the single chlorine radical? I mean, as an atom, can you isolate it?
no.
No. That's why we don't write it. Simple. We do not
Okay.
write that Cl just because we cannot isolate it. Got it? If you
Yes,
were
sir.
able to isolate, isn't it? Then you do
Hmm.
not call it as a radical anymore. Correct? Because you
Hmm.
are not able to isolate them or store them separately. It's not like I
Hmm.
can store all Cl dots, in a stack of
Yeah.
tube or something. Correct? I
Hmm.
can't do that. So that's why you do not use that terminology, because I do not get an atomic radical as is. A radical, I mean, chloride as a radical only is observed from the chlorine molecule, because
Hmm.
I have to break that, convert into that atomic form. Okay. But
Okay,
notice
sir.
this, because you are gaining that from chlorine molecule, you have to provide a lot of energy. And where
Hmm.
did that energy go? It got absorbed by that chlorines only, right?
Hmm.
And that's why now this radical word is used, because it is extremely unstable.
Okay. Okay.
Got it now?
Yes,
Right.
sir.
Now, this chlorine radical, as it reacts with the alkene, okay? Why, sir?
Hmm.
Why not? Because it's a highly energy particle now. High energy particle, when it collides with the other particle, it has a high chances that it will break it. Got it? Now,
Yes,
when
sir.
this chlorine goes and tries to hit onto the methane, this Cl dot will take away H dot from it and
Hmm.
push another radical, which is CH3 dot.
Hmm.
And again, CH3 dot becomes highly energetic now.
Yeah, because it's
And
a
that
radical.
can go and push to the neutral chlorine molecules and
Hmm.
take one chlorine inside and leave behind one more chlorine radical. And can you
Right.
see there is a cyclic process now?
Yeah.
So chlorine radical is making methyl radical is making chlorine radical, and that circle keeps happening all the time.
So for this reaction to take place, we only require one chlorine radical, and then everything will just take place on its own.
As long as, let's say, you have 100 particles of methane.
Okay.
Sorry. Imagine I have 100 particles of methane.
Hmm.
So I require at least 50 particles of chloride, right?
Right.
Chloride molecules, isn't it?
Hmm.
Because one will convert into HCl, the other one will convert into CH3Cl. Okay.
Hmm.
So the ratio should be at least 1:2.
Okay.
If it is less amount, you will get only small composition of methyl chloride forming. Rest of them it's still remaining as methane only.
Hmm.
Clear now?
Yeah.
Because you're not accounting for this HCl formation. Because every time this Cl dot goes away, one HCl is lost, right?
Hmm.
You are only looking at, sir, this Cl dot is coming here, but that Cl is also lost.
Yeah.
So again, the Cl is being generated from a new molecule of chlorine.
Hmm.
Got the point?
So if you take chlorine radical in excess, or like chlorine in excess, then won't
Correct.
the reaction continue? So you get like chloroform and all of that.
Yes. In that case, what happens, if you take chlorine excess, this
Hmm.
CH3Cl will also go attack another Cl dot.
Yeah.
Okay. And that, sorry, Cl2. I meant to say Cl2. And that
Hmm.
will again become CH2Cl2.
So you
So it
keep
will
losing
keep on
hydrogen.
happening till it becomes CCl4.
Yeah.
Okay. So
Yes.
if chlorine becomes excess, your final product is not methyl chloride, it will become carbon tetrachloride, CCl4.
Hmm.
Got it? So because that will
Yes.
keep on happening. See, these reactions are extremely controlled by temperature and light.
Hmm.
Okay. So you could even having an excess amount of chlorine, suddenly you switch off a light after some time. What happens? You might still have a
Yes,
lot
sir.
of composition of methyl chloride.
Yeah.
Got it? So it
Yes,
is
sir.
highly controlled reaction. So you could get methyl chloride, you could get carbon tetrachloride depending upon how much time you spend, how much light you pass on. Okay.
Okay.
For now, we are assuming that they are very much in proportions. Chlorine and methane are very much in proportions. So the chances are methyl chloride formation is observed the most. Got it? Right.
Yes, sir.
Now listen, the reaction is not ended yet. In even after forming methyl chloride, you might always have some amount of CH3 dot, some amount of Cl dot might be left. Okay.
Yeah.
Now, when you completely switch off the light and leave it for some time, what happens? Whatever the radicals that are left over, they will quickly combine with each other to start forming some extra molecules.
Hmm.
Got it? And these are very less in composition because most of them is converting into product. But very small number of radicals might be left over, and they might immediately, whoever is the nearest, they'll start attacking them and start forming a molecule. And
Right.
these products will be formed in traces, which means in a very, very small composition. Okay. So this mechanism is categorized into three set of steps. The first one is called chain initiation, where the
Hmm.
radical is generated. Second one is called chain propagation, where a radical is creating a new radical. See, this
Hmm.
radical is creating a new radical, this radical is creating a new radical. Okay.
Hmm.
And lastly, chain termination, where all the radicals are combining to form a neutral molecule.
Okay.
In these three reactions, the most important steps are chain propagation steps because these two are the steps which it will take some time. Why?
Hmm.
You have to generate one radical to another radical. It is not a stable product you are getting, right? You are again
Right.
generating a radical. So it will take some time.
Hmm.
In chemical reactions, if there are multi steps, okay, if there are multi steps, and out of those
Hmm.
multi step, one of the step is the slowest step. That step is called rate determining step. I'm sure you have the
Yeah.
kinetics
So
at this week, so that
yeah.
that is something you must have learned it already. Okay,
Hmm.
so rate determining step is the slowest step in the kinetics, isn't it?
Yes, sir.
So I'm saying these two steps are the rate determining steps which will decide whether the reaction will properly happen or not.
Hmm.
Okay, so now notice that since these two are the steps, now if you have noticed something, whenever we talk about the spontaneity of the reaction, whether the reaction would happen or not, we
Hmm.
always evaluate using delta G value. What is delta G? Gives free energy
Gives
of
free
the
energy.
system.
Yes,
In
sir.
a system, a chemical reaction is a system. In
Hmm.
the system, if delta G of the reaction is less than zero, then we say this reaction could be spontaneous.
Right.
Now, whether this delta G is less than 0 or not, that depends upon this formula, because delta G is defined on this formula delta H minus T delta S.
Hmm.
Okay. If this is negative and delta S is 0, then most likely the delta G will be negative.
Right.
And if delta G is negative, that means the reaction is spontaneous.
Yes.
Perfect. Now,
Yes, sir.
notice this. When it comes to these two reactions, right? These two
Hmm.
reactions, can you notice that there are two reactants and there are two products?
Hmm.
Which means there is not much of a gain or loss of entropy. Entropy
Yeah.
always depends on number of particles.
Hmm.
The number of particles are literally same. So
Yeah.
I could say there is hardly any change in entropy, correct?
Correct. Yeah.
And since this is 0, so delta G only depends upon delta H factor.
So if
And
delta
this
H is
has been
negative, then
noticed for delta H for all the halides. For
hmm.
the halides, the first step, these are the delta H values. For the second step,
Right.
these are the delta H values, experimental values.
Hmm.
Everything is in kilocalories.
Yes,
These are
sir.
all in kilocalories. Okay. Now, what have you noticed? Fluorine relatively has very high delta H1 and very high delta H2 value. Okay.
Right.
Why is that so? See, in the first step, you will notice that HX bond is forming.
Hmm.
Okay. H and fluorine is an extremely strong bond. Because of high
Yeah.
electronegative difference, it will make a very, very strong bond. Okay.
Hmm.
Now, if you notice, if a bond is very strong, energy will be released.
Right.
That's why in the case of fluorine, huge amount of energy is released. Not just that, when it comes to F2 bond, F2 is a highly unstable bond because it will
Yeah.
have 3 lone pairs strongly repelling it with each other. It is easy to break this bond, correct?
Yes,
And
sir.
because this bond breaking is easy, and this bond, carbon fluorine, is a very strong bond again
Hmm.
energy is released. That's why
Hmm.
you will notice in the case of fluorine, the first two factors have very high amount of energy released. Overall, it is minus 101, isn't it?
Yeah.
Similarly, when it comes to chlorine, the first reaction, because HCl is not as strong as that of HF, you will see some amount of energy required. But in the
Hmm.
second step, chlorine bond is also weaker, but CX bond is stronger. You will see
Hmm.
overall energy is released only.
Yeah.
In case of bromine, again the first step is difficult, second step will still release enough energy. Overall
Hmm.
makes it negative only. But lastly, if you notice iodine, this factor is so high that overall energy is positive.
So, sir, I have a like just I just
Yes,
want to
please
ask
go.
something.
Mhm.
So HI will have a weaker bond, but considering
HI has weaker bond, perfect, very weak bond.
huh. So I just wanted to, make sure of
Hmm.
that, considering the numbers.
Yes, yes, okay.
Hmm.
That I have written it at the bottom, you can see it. Okay.
Acha, okay.
So from here, what is that conclusion I can make? First thing I can make, because this is releasing huge amount of energy, F2 in the overall reaction will be the highly reactive halogen.
Right.
Then comes chlorine, then bromine, iodine, correct? So the trend of reactivity for free radical mechanism is this. Is that logic clear?
Yes, sir.
Second, the bond dissociation energy experimental value is chlorine highest, then bromine, then fluorine, then iodine,
Hmm.
bond energy wise. And bond strength of halogens, H and halogen is HF greater than HCl, HBr, and HI.
Hmm.
Using these energy terms only, we were able to conclude this, which is being more reactive and less reactive. Now, you know that carbon carbon bond breaking requires approximately 50 kilocalories of energy. Single bond.
Right.
Carbon carbon
Right.
single bond. Okay. Carbon carbon double bond requires around 70 kilocalories of energy.
Yeah.
Now, have you noticed fluorine is releasing how much energy? Minus 101 kilocalories. which is more than the bond energy of carbon carbon, more than the bond energy of carbon double bond carbon also, isn't it?
Yeah. Yes,
इसका
sir.
मतलब, if I take a hydrocarbon, something like a propane,
Hmm.
propane has carbon carbon bond also, carbon hydrogen bond also. So
Right.
if one hydrogen is replaced by one fluorine, right,
Hmm.
that's what is happening in a overall reaction, correct?
Right.
Then the energy release will be so much that it can even break carbon carbon bond also, right?
Right.
And that's the reason why fluorine is an explosive reaction, extremely high reactive. Okay,
Hmm. Yes, sir.
so that means it can break all the kinds of bonds now. If it is breaking all the
Yeah.
bonds, it is like a chain reaction, so it becomes
Hmm.
explosive, isn't it?
Okay.
Clear?
But
While, hmm,
so how explosive? Like, is it like a bomb or
no,
um?
no, not that kind of explosive form. Okay. Hmm.
Okay.
I meant to say it is able to break everything into radical forms. It is uncontrollable.
Yeah.
So it's
Okay.
not like
Okay.
you cannot say, hey, I'm able to get this product.
Hmm.
It's like a plasma state. सब कुछ radical में ही है. Got it?
हाँ.
It's very difficult to assess कि क्या product बनेगा.
Hmm.
Okay? That is what
Yes.
it meant by uncontrolled reaction. Okay? Hmm.
Yes, sir.
Now, on the other hand, iodine is reversible reaction, because you can see it appears to be that it has delta H being positive. So whatever
Hmm.
the product is forming, that is possibly again going back to the reactant,
Yeah.
isn't it? Which means if this is the overall reaction in light, that is methane plus iodine is giving methyl iodide and HI.
Hmm.
Okay, it is a reversible reaction and highly backward reversible, isn't it?
Hmm.
Now, if a chemical equilibrium is present in a reaction, how would you favor a reaction to go forward direction? You would apply Le Chatelier's principle, isn't it?
Right.
As per Le Chatelier's principle, if I'm able to remove the product somehow, I'll be able to increase the reaction more into the forward direction.
Right.
Correct? So,
Hmm.
out of this reaction, imagine every time HI is forming, instantly this HI is getting consumed.
Right.
Then the reaction can be pushed in the forward direction or not.
Hmm.
Correct? And how
Yeah.
can we do that? The minute HI is forming, right, you immediately keep that in an environment of oxidizing agent.
Hmm.
Oxidizing agent is something which can oxidize HI and convert that to I2,
Yeah. Correct.
right? So every time you make this reaction, you keep this at a high pressure of HiO3, HNO3 or HGO environment. These are mild oxidizing agents. They have
Sir.
the strength to convert
Hmm.
HI to I2. Yes, Vita, tell me.
So what about red phosphorus? Because in hydrocarbons they do use that to um prevent iodine from going back and just reversing the reaction.
Now, if you notice that red phosphorus plus I2 will become Pi3, correct? This is what it
Right.
will make it, correct?
Yes.
Now, this Pi3 somewhere is not helpful here. Why? Because if I make this Hi to convert into I2, now
Hmm.
I2 is becoming reactant, na beta? So
Acha.
increasing reactant concentration,
Hmm.
decreasing product concentration is a double advantage to move the reaction in the forward direction.
Okay. Yeah.
Is that clear?
Yes,
Right.
sir.
That's why you need to use those oxidizing agents which could create I2 more than
Hmm.
creating something like Pi3.
Okay. Yeah.
Got it? So
Yes,
that's
sir.
the advantage we will have here. Okay. Hmm.
Yes, sir.
Now, so you got a story of fluorine and iodine, right?
Yes, sir.
Now let us see the story of chlorine and bromine. Okay. Chlorine and bromine are best to be assessed here, and they mainly have something called reactivity and selectivity in process.
Hmm.
When do we use this terminology? See, I use the terminology reactivity when it is actually the reaction is happening quite fast and it is not focusing on what type of product it is getting. which means
Okay.
imagine there is an option of buffet of products out of which
Hmm.
there is something which is very stable.
Hmm.
Got it? When I use the terminology reactivity, my sense is not checking out which is most stable product. My sense is which one can form faster.
Oh, okay.
So whenever you think about reactivity, this terminology, that means you
Hmm.
are always thinking about kinetic property. Kinetic property is
Right.
related to speed.
Hmm.
Okay. And
Yes.
chlorine has this ability more than selectivity. Selectivity means you are trying to select which is more stable. Let me go in that direction.
Hmm.
Got it? So
Yes,
when
sir.
it comes to these two factors, reactivity is the factor which is more prominent with chlorine.
Hmm.
Got it? So it is
Yes.
more reactive and it is less selective.
Hmm.
Clear? So therefore, it is going to be kinetically favored product.
Right.
Kinetically favored means which is favoring speed.
Hmm.
Now, on the other hand, when it comes to bromine, it is more selective and less reactive. That means it's not looking more for how fast or how slow reaction is. It's mostly emphasizing on which is forming a more stable product or what is the
Right.
direction where I'm getting a more stable product.
Hmm.
Got it?
Yes, sir.
Why? The value itself will suggest because see the value is not this is spontaneous but not very highly releasing energy, correct?
Yeah.
So that means it will always choose in the direction where
Hmm.
the energy difference is logical, isn't it?
Hmm.
The reactant and product energy difference should be at least more than minus 6 degrees.
Yeah.
Got the point?
Yes,
Right.
sir.
So, therefore, chlorine is more selective, reactive, while bromine is more selective.
Hmm.
Okay. This can be showcased using this experiment. Notice that if at all I take propane, react with fluorine, chlorine, bromine.
Hmm.
Okay. Well, fluorine, when you do a very controlled reaction, again, you see here it has to be very controlled. Otherwise, it is uncontrollable.
Yeah.
It will immediately break all the carbon-carbon bonds also.
Hmm.
Okay, if I very reasonably give thoda amount of photons to that,
Hmm.
then I might get almost this, you know, propyl fluoride of
Hmm.
around 75 percentage and 2-fluoropropane has around 25 percentage,
Hmm.
which means this reaction is most kinetically favoring,
Most
isn't it?
reactive.
Which means it is more reactive. Of course,
Yeah.
F2 is very reactive, so it will only look out for what is the fastest way I can attack. Okay.
Hmm.
Obviously, if you have a molecule like this, and there are two hydrogens here, there are three hydrogens here,
Yeah.
which is most likely to be exposed beta terminal carbons, right?
Right.
So terminal carbons are fast and easy to approach.
Hmm.
That's why radicals will approach those areas and convert them into products.
Right.
Clear? On
Yes,
the
sir.
other hand, when it comes to chlorine also, you found this is 45 percentage and 55 percentage. That means not it is very, I can say, highly favorable towards kinetic or highly favorable towards thermodynamic product, correct?
Hmm.
But when
Right.
it comes to bromine, you will see 97% only is on secondary position. You'll hardly see this, and that is around 3 percentage, correct?
Right.
Which means bromination typically happens to give a product which is highly stable form out of all
Okay.
the products.
Yeah.
Okay,
Yeah.
clear now?
Yes, sir.
Right.
Understood.
So when it comes to the product formation, how do we assess the bromination? You always check out the stability of radicals. Correct?
Yes, sir.
Now, out of all the stability of radical, this is the order you need to remember. 3-degree phenyl radical,
Hmm.
2-degree phenyl radical, 1-degree phenyl radical, and
Hmm.
then 3-degree carbon, 2-degree carbon, and 1-degree carbon. This is the order in which the stability varies.
Okay, sir.
Are you comfortable with this point?
Yes, sir. I understood.
Sure now? Okay,
Yes,
very
sir.
good. So, so you always look out for the stability of these radicals, and that's the position where you will put the bromine. Okay.
Hmm.
For example, notice this case. If this is a reactant given, okay, this is phenyl propane. Got it?
Mm.
And when you react bromine and HNO, which is the most stable radical position? If I get a dot here, dot here, dot here, and one dot on phenyl also, the most stable position is this one, isn't it? Benzyl position, because you will have resonance there.
Mm.
This is how, if at all I get a dot here, this dot can make resonance stabilization inside the benzene ring.
Yeah.
Just like carbocation, how you have carbocation, you'll make a resonance. The radicals
Yeah.
will also make a very similar resonance. Okay.
Okay,
So
sir.
which means it is very, very stable at this position, isn't it?
Right.
So that's where you will push the bromine and make it as major product.
Okay.
Anna clear beta?
Yes, sir. I
Right.
understood.
Very good. Okay. So when it comes to bromine, you will always check out this case.
Mm.
And if the question is something different here, if the JE question more
Mm.
than major product, if it is emphasis of possible products. Imagine if the question was asked,
Okay.
how many
Mm.
possible products you have? So what you do, let's take this example. If I have N-butane reacting
Mm.
with Br2 and HNO, and I were asked how many possible products you can get. So first of all, list out all the radical positions here. One is this radical position. The other one is this radical position. These are the two radical positions I can get. And that's where I need to put bromide.
Mm.
Okay. So I would be getting two products here. One is this one, the other one being this one, isn't it?
Right.
And since when you are using the terminology possible products, you have to look into more structural kind as well as stereo kind,
Right.
right? Now notice this one. When you have, this particular carbon, have you noticed that this carbon has four different groups: methyl, ethyl, bromine, and one hydrogen. If I haven't written anything, that means
Mm.
there is hydrogen on it.
Yeah.
Correct? A
Yes, sir.
center with four different groups. What do we call it? Chiral carbon. I'm sure you're
Correct.
aware of this term. Correct?
Yes, sir.
Right. So, what I'm generating in this case is a chiral carbon. Okay.
Mm.
And you know that when it comes to, let's say, this is where the chiral carbon has cropped up from. But
Mm.
if I recall, what is the hybridization of this carbon when it is in a radical form?
SP2.
sp2.
Yeah.
Okay. Because only three bonds are there, three sigma bonds are there, and one p orbital is pure leftover. So what is involved? S and two p orbitals are involved in hybridization,
Yeah.
which means an sp2 carbon will be a linear species, right, beta? So this is
Correct.
a
Yeah.
linear species, correct?
Mm.
With one lobe above and one lobe below
Will.
that planar surface, isn't it?
Yeah.
So now Br dot, when it is accessing, it has the ability to attack from the top or attack from the bottom of this plane,
Mm.
isn't it? So
Yes,
when it
sir.
is attacking from the top of this plane, probably I might get a structure like this. When it is
Mm.
attacking from the bottom of the plane, probably I'll get structure like this. And what you would notice reasonably, when this carbon becomes a chiral center, when there are four different groups, attacking from the top and attacking from the bottom does not create same products. They will
Right.
create two different products. Now these
Mm.
two products are different together altogether. Got it?
Yes, sir.
They are mirror images of each other, but they are
Yeah.
not identical. And
Yeah.
this is the property you will notice when a carbon has four different groups.
Yeah.
Got it? For
Mm.
example, if at all I take my left hand and right hand, okay? If I tell you, are these two identical? Forget about ring and everything else, okay? Just think
Mm.
in a broad way. If you take these two hands, can you say these two are identical or not? Or they can
No.
superimpose or not, right? Now, in
Mm.
that case, what should run in your mind, Sir, are you talking in two dimension or are you talking in three dimension? Because if I put them in two dimension
They're not
in the
identical.
same plane, I can never mix them. See, no matter
Yeah,
however I turn, I can't do that. But if I do the same thing in three dimension, exactly I'm able to superimpose,
right.
isn't it?
Yes,
So
sir.
here there is one clarity you need to notice, Shana. Every planar particle is always going to superimpose with its mirror because you are talking only about three
Huh.
dimension now, correct?
Right.
So if it is planar molecule means by default its mirror image will be superimposed,
Okay.
correct?
Yes, sir.
But if it is a three-dimensional molecule, if it's a
Hmm.
three-dimensional molecule, and if it has four different groups on a carbon, then these two particles, the mirror images, can never be superimposed.
Okay. So
All
can
right.
you repeat that? Like your voice
Let
cracked
me
a
show
little.
you that instead. Okay.
Yeah.
Suppose if at all I have a three-dimensional molecule here, this representation shows it is going inside the plane. This
Hmm.
represent shows it is going outside the plane. Now imagine I have a carbon which is connected with four different groups A, B, C, D.
Yeah.
Now, if at all I take the mirror image of it, so how does the mirror image typically looks like? Like this, with uh, this B going inside and this C coming outside. C, B, A, and D. Bravo.
Yeah.
This is what you will get.
Yes, sir.
Now tell me about this, bacha. These two are mirror images of each other, correct?
Yeah.
Okay. Now, if at all I want to bring this and try to superimpose with this one, correct? So
Hmm.
what happened? This A and D, whenever I turn it around to superimpose, I need to
Hmm.
bring it and put it on this one, right?
Yeah.
So A and A I mixed to
Hmm.
put the same position as D as I start rotating around because this is how it is, correct? See, this
Yeah.
is A, this is D,
Hmm.
okay? And then I have B and C like this. This is B, this is C. C
Yeah.
is coming towards me, this thumb is C, and
Hmm.
this forefinger is B. Okay, this
Hmm.
is how it is. Now, if at all I have to superimpose that, then I have to rotate it this way or no?
Right.
So when
Yeah.
I rotate, where is C now? Going inside.
Yeah.
And where is B now? Coming outside.
Outside.
But what is in the original structure? B is inside and C is outside.
Hmm. Oh, acha, so they won't be able to
So can you
superimpose.
make that these two molecules are identical? Can you ever make it?
No.
No. Now listen. How would I make it? That how can I convert one to the other? The only way is to break these two bonds and rearrange them, isn't it?
Right. Yeah.
Correct?
Yeah.
Now let me spill over the basic definition of stereoisomers. Got it?
Hmm.
Stereoisomers are those isomers, right? Which are same in structure, they look same in structure and their spatial distribution, but their orientations are different.
Okay.
Understood?
Yes. Yes.
So now can
Understood.
you notice their orientation is the only part which is different. Now, if
Hmm.
you want to make them in the same orientation, then I have to break the particles, right?
Right.
And when you say two compounds are isomers, then to interconvert one another, you should be breaking the bonds. Then only you call them as
Right.
isomers.
Right.
So I cannot convert this to this just by rotation, isn't it? Just
Yeah.
by molding that, can I convert it? No.
No.
I have to break the bond only, isn't it?
Yes, sir.
That's when these two mirror images, which are non-superimposable, this is the terminology you should learn to use now. Non-superimposable. Okay.
Yes, sir.
So these two are
Oh,
non-superimposable and these are mirror images of each other.
so can you just write the thing about the stereoisomers also?
I have a complete notes on it. Don't worry. Stereoisomers notes I'll provide you. Okay.
Yes, sir.
Clear?
Okay.
Right. So don't
Yes.
worry about it. That has all the examples, how to view it. Everything is there in it. Okay. So don't worry
Hmm.
about it. Because this topic does not relate there. I'm only giving the glimpses. I told you that
Yeah.
isomerism, I'll do it thoroughly
Hmm.
once I'll find out these are the areas I need to focus more. Now I'm getting the idea about where you are getting confused or so. Okay. So I'll keep that in mind. And whenever we do isomerism, I'll emphasize that. Okay? So don't
Okay,
worry.
sir.
So now notice it. These two are non-superimposable and
Hmm.
these two are mirror images of each other. Correct?
Right.
And most importantly, this molecule is optically active. This is also optically active. What does this mean?
You
Suppose
can see it.
if I no,
Hmm.
it's more than that. It's a little complicated. Let us imagine this molecule.
Hmm.
I convert into a liquid state and keep it like this in a bottle. Okay, a
Hmm.
transparent bottle. Okay,
Hmm.
then I pass a plain polarized light, a light which only
Hmm.
goes in one direction. Now, the white light
Okay.
which is falling in is going in all directions.
Yeah.
If the light goes only in one direction, it is called plain polarized light.
Hmm.
Okay, beta. So now
Yes.
imagine the bottle is here. A plain
Hmm.
polarized light is coming this way.
Right.
Okay, it is striking it here. But
Hmm.
when it is coming out of this, it is going this way. It's not
Right.
exactly coming out the same way it came in. When it is
Refraction.
coming out, it is getting refracted.
Yeah.
Okay. See, water, please understand, in water, if you put a light, refraction happens inside the water. But when it is coming out, again, it will come with the same angle.
Yeah.
So, water is not active, optically active. Got it?
But I didn't get it. I didn't get it. So in
Listen,
huh.
if I incident light in water like this with an
Huh.
angle of, let's say, 30 degrees,
Yeah.
inside it might get refracted maybe by 15 degrees or 60 degrees, whatever it is.
Hmm.
But when it is coming out of the water, what is the angle it will make again?
Tea.
30 only, no?
Yeah.
It is not going to change, right?
Hmm.
So that means water is in active solution.
Oh, okay. So
But
if
if
something doesn't
this
have a
solution,
refractive index,
whatever the refraction it may happen inside,
huh?
if I'm passing an light with 30 degrees, but
Hmm.
outside when it is coming with, let's say, 40 degrees or 60 degrees,
Oh.
then that solution is optically active.
Oh. Okay. Okay.
Clear?
Understood. Yes, sir.
Right. So now every organic particle which has this chiral center with four different groups has this amazing property that it can change the angle of that light when it is coming out of that. Okay.
Okay.
So thus this compound is called optically active. It is optically active. Clear?
Yes, sir.
Now, if you have these three properties for two molecules, if they are non-superimposable, as a pair I'm talking, if this pair are non-superimposable mirror images and both are optically active, you call them as enantiomers.
Oh, okay.
So
Yes.
keep that in mind whenever you think about enantiomer. What are the three important properties that should come to your mind? They should be non-superimposable, they should
Optically.
be mirror
Okay.
images of each other, and most importantly, they should be optically active.
Yes.
Got it?
Yes.
If they are non-superimposable and mirror images, usually they will be optically active.
Hmm.
Okay. But if I do the other way around, okay, if they are mirror images and if they are optically inactive, they are definitely going to be superimposable.
Hmm.
Understood now? Let me tell
Yes,
you
sir.
again. If they are mirror images and if they are optically inactive, then
Then be
both
super
will be
important.
definitely superimposable. Okay.
Yes. Yes,
Now
sir.
you notice that the superimposability is precisely depend on this character, right? Optically
Right.
active character, isn't it? If it is
Hmm.
optically inactive means they are superimposable. If they are optically
Right.
active means they are
Uh,
non-superimposable. Correct?
non-superimposable. Yeah.
Now this property is called as chirality.
Oh.
Mhm.
Okay, wait. So it just doesn't depend on how many groups it's attached to. It's also
Ah,
dependent on optically active or inactive.
yes. Okay.
Okay.
So
Yes.
a chirality is a property of a molecule, intrinsic property.
Hmm.
Okay. It is a intrinsic property of a molecule that
Hmm.
if it is showing chirality, that means you are expecting it to be optically active.
Okay.
If it is optically active, then its mirror image has to be non-superimposable.
Hmm.
Clear, beta?
Yes,
So
sir.
always revolve around these four words, very important words. One is C, chirality, optical
Hmm.
activity, mirror images, superimposability.
Hmm.
Okay?
Yes.
Always try to relate these four. It will be very, very useful for you. Okay?
Yes, sir.
Okay?
Yes,
So
sir.
if particles are chiral, that means it is showing a property called chirality.
Yeah.
And what is a property called chirality? It should rotate plane polarized light.
Hmm.
If it is rotating plane polarized light means it is optically active.
Right.
If it is optically active, its mirror images are
One super.
non-superimposable.
Yeah.
You got the circle now?
Yes, sir.
Correct? Try to repeat on yourself once how it is.
Okay. So, if something is chiral, then it exhibits chirality, and it is able to rotate a
Plane polarized light. Hmm.
yes, plain polarized light.
Mhm.
And if it is able to do that, then it is optically active.
Perfect.
And since it is optically active, it is non-superimposable.
Perfect. Their
Their
mirror
mirror
images. Their
images are
mirror images
non-super.
are non-super.
Yeah.
Perfect. Okay.
Yes,
Always
sir.
go with this flow. Okay.
Yes, sir.
And if these three properties are being evaluated for a pair, then they are called enantiomers.
Enantiomers.
Clear? Right.
Yes, sir.
Now, have you noticed something? What we got here, these two products, what we got are actually enantiomers,
Yeah.
isn't it? Now, imagine if I'm getting these products, obviously, I don't know whether I'm getting this one or this one. Chances are I'll get 50% of this, 50% of this, correct?
Hmm.
So, if I take this entire thing in a solution and try to see the light, this time there will not be any optical activity. Why, because
I.
I'm not taking only this particle or only this particle. I'm taking half and half of this, right? 50% of this and
Yeah.
50% of this. So imagine
Hmm.
like this 50% is trying to make an angle of 10 degrees. What will this will do? This will try to make an angle of minus 10 degrees.
Oh, so it will cancel out.
Yes, it will cancel off with each
Huh.
other. So as a solution, mixture of solution, that
Hmm.
solution appears optically inactive.
Okay. So then
So
you have to look
individually
at
this is active, this is active. But
hmm.
as a solution, if you take 50-50%,
Yeah.
solution is optically inactive.
Hmm.
Clear, beta?
Yes, sir.
So if an optically inactive solution is made out of 50% each of enantiomeric mixture, that is
Hmm.
called racemic mixture.
Okay. Okay. Understood.
Clear now?
Yes, sir.
So what I'm getting is a racemic mixture. Clear, beta?
Hmm.
So see how the questions are framed. If the question is asked how many number of possible product, one is this one, there is no chirality here. One
Hmm.
is here, there is a chirality here, and there
Right.
are two products forming. So if the question is asked how many possible products, answer is three. Okay.
Okay. Huh.
And
Yeah.
if the question is asked how many optically active products, answer is two.
Right.
Okay. If the question is asked, is the
Hmm.
final solution optically active? Answer is no.
No.
Got it? Why? Because this is not coming, 50-20 or 80, 80-20 or 20-30-70 like that. It is coming exactly 50-50. So because it is coming 50-50, it will be optically inactive solution. So
Ah,
be very careful how the question is framed. Whether it is
yes, sir.
asked optically, whether it is asked about solution, whether it is asked about individual elements, correct?
Mm.
So that way you
Yes,
have to be clear. Understood now?
yes, sir.
So for this
Understood.
case, how many products we got? Three. Okay.
Yes, sir. So just one question.
Yes, ma'am.
Um, so if the percentage was not equal, then it would be optically active.
Optically active. Yes. It will be
Yeah.
optically active. Yes. Mhm. So you could notice that the final solution is optically inactive due to racemic mixture. Total number of isomers, including stereoisomers, are three. Total
Mm.
number of fractions that can be distilled from the mixture is two. Now, what is this one? Last one. See, what do you mean by number of fraction distilled? See, if imagine I got the solution, I got three compounds, right? Here I got three compounds. Usually
Yeah.
we write it as plus and minus, which means if one is positively rotating, the other one will be negatively rotating. So
Mm.
total I have three products.
Right.
What if I take that liquid mixture and
Mm.
make distillation?
The racemic mixture won't be distilled, I
Yes,
think.
it cannot be
Oh,
distilled. Why? Because enantiomers structurally they are exactly same, right?
right.
Enantiomers are structurally
Yeah.
exactly same. Only the
Yeah.
orientation is different, isn't it?
Mm.
So since they are structurally same, they would have same boiling point, they would have same melting point, they will have same density, they will have same physical properties.
Mm. So you
I meant
can't
to
distill
say
them.
this one and this one, these two will not have any difference in their physical properties.
Mm.
And distillation is a physical separation
Yeah.
based on boiling point. If the
Mm.
boiling point of this is X, this will also be X. So how can we separate
Yeah.
them? We
So they'll
can't.
come out mixed.
Yes, they'll always come out mixed. So,
Mm.
which means when I distillate them, how many fractions I'll get? I'll get two fractions. One fraction in which I'll have this compound, the other
Yeah.
fraction I'll have this compound. This
Mm.
is what I meant number of fractions. So these
Okay.
are three typical type of questions that will be directly asked to you. Okay. How many
Yes.
isomers, whether it optically active or inactive solution, and lastly, how many fractions.
Mm.
Let us try to decode the same with another example, a better example. Okay.
Okay.
So check out how many substituted products are formed on monochlorination of this compound. Okay.
Yeah.
How many monochlorination products you can get. Check out.
Mm.
Now here and here, I need to be very precise. Alkyl substituted. How many alkyl substituted? Because otherwise you might think on benzene also it can substituted. Benzene is
Yeah.
used the terminology aryl. Aryl
Mm.
means on benzene. Okay.
Yeah.
Alkyl means only on sp3 carbon chain. So
Okay.
check out. So in this case, where are all the locations, beta? This is a new location, new location, new location, new location. So therefore,
Right.
four different locations are present, isn't it?
Mm.
At four different locations, I can get chlorine. One chlorine can come here, one chlorine can come here, one here, and one here. Okay.
Mm.
Once you get, now notice it carefully. Have you noticed after chlorine has come here? In fact, before also it was a chiral center only.
Yeah.
Now after chlorine coming also, the chiral center is retained.
Mm.
Here also it is chiral center. This is also chiral center. Are you able to identify that chirality and chiral center?
Oh, yes, sir.
Comfortable, right? Right.
Yes, sir.
And similarly, this is also chiral center. And
Mm.
eventually, this is also chiral center, correct?
Right.
So, for this one chiral center, how many isomers I'll have? Two.
Two.
Now, if at all I have two chiral centers, how many isomers I'll have? Four.
Four.
And if at all I have one more chiral center, how many I'll have? Two.
Mm.
And one chiral center, how many I will have? Two.
Two.
So, total how many products I will get? 10.
Okay.
So
Yeah.
the question
10.
is asked how many number of products including stereo. So answer is 10.
Mm.
Second question, how many number of enantiomeric pairs are present in it? You only tell me, think.
So the answer's right there.
No, no, I mean think in terms of you whether you are able to justify that out.
Um,
You can see the answer, but try to justify it. Are they correct or not?
Wait, so can you go back to the previous example? I want
Yeah,
to
sure.
just. So I'm not understanding how it would be five. Like, um, each would have. So the first one would have two, and then the
Correct.
next one would have
Four.
no. The first one would have one enantiomer pair, and the second one would have two,
Two pairs.
and third and fourth will have one.
Correct. So total
Okay,
how many we got?
so
Five only, na?
five.
Hmm.
I was unsure.
Got it?
Yes, sir.
Right. So you got five. Next, how many fractions I will get? Can we separate enantiomers?
No, so
So there you go. You have your answer. So how many
right.
enantiomeric pairs you
Yeah,
got? Five pairs, right?
yeah,
So
five.
only those five will be separately coming. You cannot
Mm.
separate within the pairs. Make sense?
Yes, sir.
And how many optically active we have?
10 only. Like,
10.
yeah,
Okay. Is the overall solution optically active or inactive?
active.
How?
No. Oh, I'm confused now. Wait.
Take your
Uh,
time. The question is the overall solution optically active or inactive?
I'm confused. Like, I don't know how to.
No problem. Let's go back and listen. Okay.
Hmm.
I said that during radical mechanism,
Hmm.
if there is a chance of forming a chiral center, okay,
Hmm.
it could happen to form 50% from the top, 50% from the bottom.
Right.
So you will get enantiomer of 50% each.
Hmm.
How many enantiomers we got? Five.
Five.
Out of those five isomers, everybody will be 50-50% each, right?
Huh. Okay, then, yeah, correct. Then it's
So
10.
it's 10. That's how you're getting
Yeah.
10. And all of them are 50-50 percentage.
Hmm.
Correct? So
Yes,
let's
sir.
say the first isomer is making 5 degrees angle with one isomer.
Hmm.
First pair is making 5 degrees angle with one isomer. What will be its other isomer? Minus 5.
Yeah. So they will
Second
cancel.
isomer, yeah, second isomer is making 30 degrees angle. What will be
Hmm.
its other pair?
30.
Minus 30.
Minus 30.
So which means every time you make this reaction, if
Hmm.
you are only getting enantiomers, if you are only getting enantiomers, will there be will the solution ever be optically active? Solution I'm talking about.
No, no, it will
No,
be inactive.
always inactive
Hmm.
solution. So overall
Okay.
solution will be always inactive. Okay.
Hmm.
Individually they are all active.
Yeah.
Individually they are all active. Okay.
Yeah.
Everybody is showing some reading. So definitely they are all
Hmm.
active. Okay. But as a mixture they are inactive. Okay.
Yes, sir.
Right. Clear? Now this is just a glimpse of isomerism. I've taken only two examples here. Okay. I
Hmm.
could take entire oceans of isomerism questions here, but this is
Yeah.
how wherever it is related, only those questions we'll try. Okay. Hmm.
Hmm.
Now let us go further. While I was discussing, you only said, "Sir, what if we have excess amount of chlorine, isn't it?"
Hmm.
Listen, if it is limited, the chances are monochlorination will be major. If it is excess, the same CH3Cl again reacts with Cl2 to form this one
Yeah.
again reacts to form this one again reacts to form this one. So
Hmm.
eventually, which is major? Tetrachloride.
Yeah.
Okay, this is
Yeah.
how the product will happen. Now, these are other type of questions that can be asked from J, and this is very commonly asked here, that find the total number of products when excess chlorine is treated with C2H6. Okay. So eventually, when you see all the products, I said major will be this, but I never said that this is not coming, this is not coming, or this is not coming. They all will be there, but major will be this one, isn't it?
Yeah.
Likewise, when it comes to ethane, what are the possible products now? Now, these are not isomers. That's why I use the word only products.
Mm.
So, check out. First, monochlorination. When you do monochlorination, chances are I'll get only one product.
Yeah.
If I do dichlorination, I can get this side, I can get this side, isn't it? Like this. Two chances are
Right.
there. If two halogens are present on the same carbon, you call it as geminal dihalides. Okay.
So what did you say about this? If two carbons?
If two chlorines or if
Huh.
two halogens are present
Mm.
on the same carbon, you call it
Mm.
as geminal dihalides.
Okay. Okay.
If
Yeah.
they are present on adjacent carbons, you call it as vicinal dihalides. Okay.
Yes.
Vic is used for adjacent, gem is used for same position.
Okay.
Always
Yeah.
this
Yes.
terminology throughout organic, wherever you see Vic means adjacent, gem means same carbon. Okay.
Yes.
So therefore you can notice here CH3, CH3 here. So you could notice again I have two chances. All chlorines on one carbon or two chlorines on one carbon, one chlorine on the other carbon.
Mm.
If you have four chlorines, I can have three chlorines here, one chlorine here. Or I can have two chlorines here, two chlorines here. Correct?
Mm.
When you have five chlorines, I can get only one chance. Six chlorine,
Yeah.
I can get only one particular
Mm.
chance. So total, how many different products you are getting? Nine different
Fine.
products.
Yeah.
Clear now?
Yes.
Right? So that is what you need to know about this structure. Okay. Now, this is the first reaction set. What did we learn? We learned that how, sorry, there is one more part. Sorry, I skipped one page here. Okay. Let me add that. Okay. Hmm.
Sir, is it 12 in the middle of the night there?
Yep.
Oh,
I'm at,
why would you stay
I'm at
awake so
Melbourne
late?
timing, no, but
Yeah.
uh, so it's 12:20 now. Hmm.
Yeah, I just saw like at the corner of your shared screen.
Where?
No, 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 here, on the
Also,
iPad screen. Yeah.
oh, 1 second, I'll do it in the presentation mode. Now you'll not see anything else. Yeah, that's fine. Yeah, that'll be distracting sometimes. Yeah, I was just having another class where I had to show two screens. Two screens are not
Oh.
possible with the presentation mode. Yes, I forgot
Mm.
to change that. Yeah. Now let's notice this one here. Whenever we talk about uh, selectivity and reactivity, okay, then we can always discuss what is the rate of halogenation halogenation at different positions got it.
Mm.
For example, if at all I have 1 degree hydrogen, 2 degree hydrogen, and 3 degree hydrogen to be replaced, because all I'm doing is removing hydrogen, replacing that with halogen, correct?
Right.
In that case, if at all I have to replace these hydrogens with halogens, isn't it? So in case of chlorine, it is noticed that 1 is to 3.8 is to 5 is the rate of chlorination. Got it? That
Mm.
means if I have 1 degree hydrogen, okay, if a chlorine is approaching there and it is
Mm.
taking, let's say, x speed, x maybe minutes per x minutes, per second it is taking. I mean to say, um, x concentration per second it is taking. Correct.
Yeah.
So if this much is the speed with which it is associating with the first position, then with 2-degree hydrogen, it will be 3.8x.
Thanks.
And
Yeah.
with 3-degree hydrogen, 5x. Okay.
Mm.
This is the rate at which chlorination would happen. While when it comes to bromination, it is 1 is to 84 is to 1600. This is the rate of bromination. Got it? This is the rate of bromination.
Yeah.
For example, if at all I have propane and I'm trying to react this with chlorine in the presence of H nu, then I can get two different products. One is a chlorine here plus one a chlorine here. Correct? These two are the possible products, beta.
Yeah.
So these two are the possible products. Okay.
Mm.
Now, if at all I want to find out what is the percentage amount of products, if you have to find out percentage amount of products, then first let me define how many alpha 1-degree hydrogens I have, how many 2-degree hydrogens I have. How many 1-degree hydrogens I have, beta? 6. How many 2-degree hydrogens I have? 2. Isn't it?
Yeah.
Correct?
Yeah.
So now, when a chlorine is going towards 2-degree position, then the percentage amount will be equal to 2 hydrogens, which can possibly be replaced by chlorine, with
Mm.
a speed of 3.8 divided by divided by 6 hydrogens with a speed of 1 and 2 hydrogens with a speed of 3. This is the total speed, and out of that total speed content, this much is the content of 2-degree, and that into 100 will suggest as what is the percentage you can get, what is the
Mm.
percentage amount you can get for this 2-degree. And if I want to calculate what is the percentage amount I should get for 1-degree, how much that will be? It will be total 6 into 1 divided by 6 into 1 plus 2 into 3.8 into 100. This will be the percentage amount of chlorine at 1-degree position.
Yeah.
Basic kinetics. Whenever you have
Yes.
in kinetics, percentage can be calculated this way, right?
Yeah.
That is the same thing I have done it here. Okay. So
Yes, sir.
now how much is the percentage? Let me just calculate. So 6 plus 2 cross 3.8, that is 13.6. So 3.8 into 2 divided by 13.6. So I'm getting this as 55.8 percentage. Okay. Which makes this as 44.2 percentage.
Mm. Yeah.
Correct.
Yes, sir.
So if chlorination is given, I can, unless calculation, it becomes difficult to say which one is major,
Mm.
because काफी close रहेंगे values, isn't it?
Uh,
हाँ.
yeah.
But if at all I do the same logic for bromination, you notice this one, this, if at all I treat with Br2 and H nu, and I would get these two products. One is Br here, the other one is Br here. Now, percentage amount of bromination will be equal to how much, beta? 2 times
Two
of 84 by,
two
right?
into 84
2
plus
into 84 plus
6
6
into
into 1
1600.
into, no, no, this is not 3-degree, it is 1-degree.
Acha, हाँ. Yeah.
Correct?
My bad.
Huh. So next, this is 1 into 6 divided by 1 into 6 divided by
Same denominator.
2 into 84 plus 6 into 1 into 100. So here it is pretty much clear that this is major, right? So
Right.
when it comes to bromination, it's very easy to figure out what is the major product. In the case of chlorination, it becomes difficult.
Yeah.
All right. Let me take one typical question which is asked in JEE Advanced. Okay. So in JEE Advanced, this question has been asked multiple times, or a very similar kind that has been asked multiple times. So
Hmm.
suppose if you have this compound treated with Cl2, H nu. I need to find out possible monochloro products with percentage of major product. Got it? So now, for this case, first I will write down how many 1 degree, 2 degree, and 3 degree are present in the first case. So you notice that
Mm.
1 degree hydrogen we have are 9, 2 degree hydrogens we have are 2, 3 degree hydrogens we have are only 1. Did you get that?
Mm. Yes, sir.
Is
Yeah.
this information clear?
Yes, sir.
Right, very good. So now let me put down the possible products. One, let me just copy this one. Yeah. So if you notice in the first case here, where is the chlorine I can keep? First, I can keep chlorine here.
Yeah.
Second, I can keep chlorine here. Third, I can keep chlorine here. Fourth, I can keep chlorine here. Okay. I think these are the 4 distinct position we have. Check. Are there any other distinct positions here?
So what about the left side?
You mean this side?
Yeah.
Isn't this and this same?
Okay. Yeah. Yes,
Same
it
only,
is.
no?
Yeah.
Right. So how many we can get? 4 different
Oh.
structural products.
Mm.
Structural. Now, if I get 4 different structural products, now let us figure out what is the percentage. Now, the percentage amount of hydrogen in this, sorry, percentage amount of chlorine in this will be how many these three. If you notice, these three positions are very distinct position compared to these three, because these three
Mm.
positions are not same. These two
Yeah.
positions are same, but this position is not same, correct? So that's why
Mm.
there are three distinct position with a rate of 1 divided by overall how many 1 degree we have. 9 1 degrees into 1 plus 2 into 3.8 plus 1 into 5 multiplied by 100. You got the point
Yeah.
now? Right. Similarly, if you
But
notice this,
so the numerator we have to take it with respect to the number of uh hydrogens, no?
hydrogens, which will give the distinct product.
Hmm.
So for a distinct product, how many hydrogens which are similar on that? 3.
Okay. Okay. Yeah.
Correct? That's the usual mistake. That's why it's a very tricky question. Okay. Got it? A lot of
Yes.
students suddenly take this as 9, which is wrong. Because
Yeah.
these 3 hydrogens are different from these 6 hydrogens.
Hmm.
Right. Next. Notice in this percentage second case here. So I'll have 2 cross 3.8 divided by the rest. The rest is the same. 9 cross 1 plus 2 cross 3.8 plus 1 cross 5 into 100. Okay.
Mm.
Similarly, if you notice here, now this time it is 6 cross 1. Understood now? Because all those 6 positions are same only, no? But these 3 hydrogens and these 3 hydrogens are same positions.
Huh. Huh. Yeah. Got it.
Right.
Got it.
That divided by 9 cross 1 plus 2 cross 3.8 plus 1 cross 5, that into 100. And lastly,
Hmm.
for this percentage, it is 1 cross 5 divided by 9 cross 1 plus 2 cross 3.8 plus 1.5 into 100. Done.
Hmm.
Now, if the question is not about exact percentage asked and it is only asked major, you can just check out the numerators. That's it,
Yeah.
isn't it? So 3 here, this is approximately how much? 7 here, approximately 7. This is
7.6.
6. This is 5.
Hmm.
So which one is major, beta? This one.
Yeah.
So 2 degree one is major in this case. Clear?
Yes, sir.
Right? So if you were asked what is the order of their products here, let's say this is 1, this is 2, this is 3, and this is 4. Okay. Percentage composition order.
2,
If
3,
I ask percentage composition order, then that is 2 greater than 3
3,
greater than
1.
4 greater than
1.
1. Done. So
Yes,
now
sir.
I hope you understood how to solve this question.
Yes, sir.
Okay, very standard G advanced question. You cannot miss out on this kind of questions. Okay,
Hmm.
clear? So if you
Yes.
understand the logic, it's very easy. Okay, any kind
Yeah.
of questions that can be framed, it will be very, very easy. First, you need to check out number of monochlorides. Acha, what if I ask you more questions in it? How many possible number of stereoisomers you get here, including stereoisomers, total isomers, including stereoisomers?
Um, Wait. 2? No. Is it 2?
No, no, four तो ऐसे दिख रहे हैं ना बेटा. Total isomers, I'm saying.
Acha, okay.
Hmm.
Sir, I'm confused. Wait.
Don't worry, but Shana, don't worry. Okay,
Yes, sir.
एकदम chill करने का, आराम से सोचने का. If you're confused anywhere, don't get panicky. You ask me, okay? I will go to any nth level, right? We will repeat it back. Do not hesitate. ठीक है बच्चा? Now,
Okay.
what my question is, listen एकदम ठंडे दिमाग से. Don't worry. What I'm asking is, how many possible products you will get? Monochlorinated products.
Hmm.
Structurally, you are able to see four.
Right. Yeah.
That there is no problem in that,
Hmm.
right? Now you need to notice whether there are any chiral centers in any one of the cases.
Okay, so
Based on chiral centers, you'll be able to figure out whether there are any enantiomers existing or not.
hmm.
Now, in the first case, tell me, is there any chiral center, beta?
Uh so there's one on the left
You mean
side.
this one?
Yeah.
No, it is not. Why? You have to tell me that also.
Okay. It has to be attached to 4 groups. So do
Four
the
different
group.
groups.
Oh, okay.
What is
Yes.
chiral center mean? Four
Four
different
different
groups.
groups. Okay.
हाँ देखो अभी गलती हुआ था आगे
Hmm.
कभी नहीं होगा आपसे. That's how you will
Yeah.
learn it. Okay. That is
Okay.
whenever you're searching for a chiral center, you would search for four distinct
Different.
groups. Right. Now tell me,
Okay.
first in the first molecule, do you see any chiral center?
No.
No. At all other positions also clear. Here also you have one chlorine, one
Hmm.
alkyl group, two
Yeah.
hydrogens. I have not written,
Right.
but there are two hydrogens. What about the second one?
Second one also doesn't have any different groups, so no chiral
अच्छे से
center.
देखो, फिर से देखो.
Okay. Uh, so can two of them be the same? Can two groups be the same?
No, if two groups are same, then it is not chiral, no? But
Okay.
you have to check on every
Uh,
carbon.
yeah. So, in the second one's there about the chlorine one.
Yes, very good. So this
Hmm.
carbon has one chlorine, one
Hmm.
methyl, one isopropyl, and one hydrogen.
Right. Yeah.
Aren't they four different groups? Chlorine, hydrogen, methyl, isopropyl.
Hmm.
Got it? So there
Yes,
is
sir.
a chiral center. Usually, I always ask students to mark it with a star or something, just for your
Yeah.
reference. Hmm. What about the next one? Here,
So, it doesn't have any.
check again.
No, wait.
Each and every carbon you have to check properly.
Yes.
Let me help you with that. First,
No,
what
no,
about
no.
this
Wait,
carbon?
wait. No, I think I got it.
Uh-huh.
Is it the one that's on the left side under this
This
thing?
one?
Yeah.
Yes.
Okay.
Methyl, ethyl, Methyl chloride. Methyl chloride is a different group than methyl,
Yeah, and
then
hydrogen.
hydrogen.
Okay.
So yes, there is one more chiral center here. Yeah,
Yeah.
clear?
Then
Right. What about the last one?
so can the chlorine position have a chiral center?
You have to tell me that.
Okay. Uh
Read out. What are the groups present on it? What is this chlorine?
Chlorine, methyl,
This is ethyl. This is methyl. This is
methyl.
methyl.
Okay, so it won't
Are
be
two
able to
methyl
be present.
groups. So
Yeah.
it is not chiral.
Hmm.
Two same groups, na beta?
Then
Methyl, methyl or same groups.
yeah.
So it is not chiral. So this is not chiral center.
Hmm.
Correct?
That doesn't have any chiral centers
Nah,
then.
no chiral center. Now tell me how many total products?
6.
Very good. So how many? 6 products you will get. Okay.
Yes, sir.
This 2025, this question has asked 2 times in JEE mains.
Like 2 times in 2 different
Two
papers.
different sessions, yes.
Oh wow.
So
Okay.
you imagine how important this question is, है ना?
Yeah.
In advance, they have asked this composition case, and in mains
Hmm.
is a very standard question of finding how many isomers. इतना easy
Hmm.
आएगा paper. Got it? Just
Yes.
that basics, if you have clear, that's more than enough. Okay. So
Okay,
you
sir.
got this now. How many isomers you got? 6.
6.
Now let me put it more. How many enantiomers are present? Enantiomeric pairs. How many pairs?
Wait. Uh, so can we go back to the notes, the about the enantiomers?
No, you only recall that.
Okay. Uh,
You're worrying about, you know, too much intrinsic details. Don't worry about that.
okay.
Enantiomeric means first check out chiral center. That's it.
Yeah.
If there are chiral centers means
So there'll be 2 enantiomers.
yes, that's it. So that is a pair, right?
4.
Right. One dot, one chiral center is there means it is definitely existing as a pair.
Yeah. So then in total there's 4 enantiomers.
Total 4 enantiomer molecules. How many pairs we
Hmm.
have? 2 pairs.
Yeah.
So this is one pair. This is one pair.
Hmm.
Right. So 2 pairs we have. How many
Okay.
optically active compounds we have?
2.
Active compounds, I said, not pairs. Or how many optical active isomers? Compounds I could use. I can use isomers.
So the ones with the chiral center won't be optically active.
No, they are optically active. No, but their mixture is not optically active.
Oh, huh. Okay. Okay.
Individually, they are all optically active only,
Okay.
isn't
Yes.
it?
So
So how many
then
optically active isomers? Answer is total
4. 4.
4. ये दो
Yeah.
है ना
And
total.
then, huh.
Yeah, these two are optically inactive. You don't have to worry about them. There is no chiral
Yeah.
center, so don't worry about them.
Hmm.
Correct. So how many
Yes.
optically active isomers? 4.
Yeah.
How many optically inactive isomers?
2.
2. Two
Yeah.
optically inactive isomers. Clear?
Yes, sir. Yes, sir.
Is the overall solution optically active or inactive?
So it's active because
Overall solution, I said.
inactive. Inactive.
Inactive. Why?
Hmm. Because the optically active ones would cancel themselves out and the other two are
Wonderful,
inactive.
wonderful. Because they
Yeah.
always form racemic mixtures. Perfect.
Yes,
Right.
sir.
So ऐसे repeat करने का हर question को. Wherever you see question, try
Yeah.
to recall these terms again and again. Okay. So you get a
Yes.
habit of it. Clear? Right. So the first reaction is done. For
Hmm.
alkanes, the first reaction is free radical mechanism. So in free radical mechanism, what all things will happen, I taught you. I hope that is clear. Right.
Yes, sir.
Now let's go to the second reaction. The second reaction of alkenes where it involves is aromatization. Okay. Aromatization.
Hmm.
Aromatization is when you take anything like an hexane and put in a tube. okay, a metal tube, okay, which is coated with these oxides, chromic oxide, aluminum oxide. Inside, it is coated with this metal oxides, and then you pressurize this hexane gas, correct? So what will happen on highly pressurizing that, this entire hexane will crumble close to each other and try to convert itself into benzene. So you could see benzene is thermodynamically very stable, high temperature sustain करने वाला group है.
हाँ.
So it will convert everything into benzene, releasing some H2 gas out. Obviously, you are making an hexane into an benzene form, so hydrogens have been lost out of it.
Yeah.
Clear?
Yes, sir.
For that, these kind of oxides are required which can sustain high temperature. How high temperature? 775 kelvins. Unfortunately, this year, this information based question was also asked. What is the temperature at which aromatization happens? So this is
But
given
I
in
think
NCRT.
people
So you
didn't
could
know
imagine
that.
line by line NCRT. Why is it important?
Mm.
Hmm? Hmm. Correct. So they ask at
Yes.
what temperature aromatization happens. Okay. And that happened this year only, unfortunately. Okay. So you
Mm.
have to remember that. Okay. So 775 kelvins at a at a pressure of 100 to 200 atm.
Mm.
Okay. At these temperatures, vanadium pentoxide, molybdenum oxide, or a mixture of chromium and aluminum oxides.
Mm.
These would really help to make the hexane into benzene. What if instead of hexane I took one heptane? In heptane, other than benzene, there is one extra carbon, right? That
Yeah.
extra carbon will convert into toluene, and that is
Mm.
major product. Clear?
Yes,
If you
sir.
have n octane, now you have two extra carbons, and two extra carbons can become ethyl or two methyls with a different positions of benzene, correct? So therefore, how many total products you will get? Four. Again, this year JE question. What are the total number of products formed? Answer is four. Correct?
Mm.
So this is ethyl benzene. Two methyl groups on benzene is called as xylene. And if they are
Okay.
adjacent, it is called ortho. If they are 1,3 position, it is called meta. If it is 1,4 position, it is called para. So this is orthoxylene. This is metaxylene. This is paraxylene. Clear?
Yes, sir.
Right. This is about aromatization. Next. What about reaction with steam? Methane, when you react with water in the presence of nickel, it will convert into water gas. This is given in inorganic. It is not given in organic reactions. In NCRT, it is given in S block elements. Got
Mm.
it? So you remember that methane, when you take steam, if you push steam at high temperature in the presence of nickel, this carbon will convert into carbon monoxide and H2 gas is released. The
Mm.
mixture of these two gases is called water gas.
Yeah.
Okay, right. Next. Next one is an oxidation of this alkanes. See, methane I'm taking as an example, but it is valid for other alkanes also. That means even if I take ethane, it will become ethanol like that. Okay.
Mm.
So if I take methane, you oxidize with O2 in the presence of copper. Acha, usually if you take O2 without any metal surface, right? Basically, how the reactions happens is you block everything with this metal surface. Carbon
Mm.
metal hoga. In that you fuse methane gas. From the other end, you fuse oxygen gas, heat it strongly,
Mm.
right? Usually, if carbon is not there, then everything will convert into carbon dioxide and H2O. That is called combustion.
So you mean copper, no? You said
Sorry,
copper.
copper. Sorry,
Huh.
copper metal is not there. Then it will
Mm.
convert into carbon dioxide and H2O. Okay, beta.
Mm.
But if copper is there, then copper will not let to get complete oxidation. It will only stop at methanol.
Yeah.
Understood?
Yeah.
Similarly, if you have molybdenum oxide, it will stop at formaldehyde.
Mm.
And if you have manganic acetate, right? And manganic acetate is a powdered form, which will be added in any metal surface. That will
Mm.
convert into formic acid. Got it? These are
Yeah.
industrially known reactions. There is no mechanism for it. You have to directly remember it. Okay. With
Okay.
copper and heat, methanol. Molybdenum and heat, formaldehyde. Manganate esters give formic acid. Okay.
Hmm.
And lastly, you alkanes do not react directly with KMnO4 except in the case of tert butane. If you have tertiary butane, then you can
Hmm.
remove this hydrogen, insert an oxygen in between, and convert that to 3-degree alcohols.
Okay.
Okay.
Yeah.
Again, this was asked last year 2 times in JEE mains. Got it? So these are
Yes.
very direct reactions, no mechanism or anything to learn, just the basic literature that you need to learn. Okay,
Okay. Yeah.
done. Next. Next reaction is nitration. Alkanes also involve in nitration. Okay, but nitration happens via radical mechanism. On heating, nitrates will always break into HO dot and NO2 dot. These are the radical breakings which you will notice. And the
Hmm.
mechanism is very similar. Like HO dot will take, when you react with CH3, it will convert into CH3, CH2 dot plus H2O. Okay. And this dot will combine with NO2 dot to convert into CH3, CH2 dot and NO2. Understood now?
Yes, sir.
Same mechanism is repeated again, just like free radical mechanism, which we had it.
Hmm.
So that way, but in here, when carbon nitrogen bond is forming, the energy released is sufficient enough to break carbon carbon bond also. That's why you will get multiple products. You will get a product with NO2 without breaking and with breaking also. If you break these two now, you'll get these two radicals. These two
Hmm.
radicals, when they combine with nitro, you will get methyl nitro,
Yeah.
nitromethane. Okay.
Yeah.
Same way, if you have propane, you can get nitropropane. You will get 2-nitropropane. You will get nitroethane. You can get nitromethane.
Hmm.
So these four possible products you will notice. Okay, beta.
Yes, sir.
Next one is sulfonation. For alkanes, sulfonation occurs with 6 or more than 6 carbons. That means if the alkanes are 6 and more than 6, then this reaction would happen better. So if
Yeah.
you react with concentrated H2SO4, this would also go through a radical mechanism, giving us a sulfonic acid. This is called alkyl sulfonic acid.
Hmm.
And here, sulfonate HSO3 dot, which you have, right? HSO3 dot. This is going to behave very similar to Br dot, which means it is highly selective.
Yeah. Less reactive.
Yes, less reactive and highly selective. So highly selective will always choose which one beta 3-degree, then 2-degree, 1-degree, and then hydrogen. Okay. So
Yes, sir.
therefore, in this case, for example, what are the possible products? You can get SO3H here, SO3H here, SO3H here, and SO3H here. Okay. Out of that, which is major? This one, because that
Hmm.
is where it is more stable radical. Clear? Right.
Yes, sir. Yeah.
Next, if you have cycloalkanes, you could react directly with Cr2O3 or Al2O3, or if your cyclohexane is already present, you can directly react with sulfur, selenium, or platinum and heat. This and heat. Okay.
Hmm.
Even the logic fits the same if you have an alkene, because this is not an alkene topic. I have not written it here, but just for a reference, I'm writing sulfur, selenium, or platinum and heat. That will also aromatize this into benzene. Okay, clear it up?
Yes,
Alkane
sir.
or alkene, everything will convert into benzene. Okay,
Yeah.
next. If you have cycloalkanes react with H2 and nickel, it will convert into simple alkanes. If you take bromine, bromine will get added on both sides. You will get open chain with 2 bromides. HCl on heating will also get added up with H and Cl.
Yeah.
And finally, if you take H nu, that means only heat, you will get an alkene and H2 gas is released. These are again straightforward reactions, simple addition reactions. Okay.
Yes, sir.
Lastly, thermal cracking reactions. Thermal cracking is when you have an alkane reacting with zinc oxide surface. When you react with zinc oxide, a part of Al2O3 and Cr2O3,
Hmm.
then if you, I mean, obviously, if you have a bigger chain like 6 and all, you will usually get benzene also into form. Okay. But you
Okay.
usually take up to 5 carbons. So 2, 3, 4, 5, these kind of carbons, if you have, they
Hmm.
all will break down into smaller particles as many as possible. So what are the smaller particles? Ethane, methane, ethene, and also propene. The smaller part of this is propene as
Hmm.
well. Okay. Anything which can be removed by hydrogen or carbon. Okay. So this
Okay.
is called thermal cracking. Thermal cracking essentially is done for crude oil. Crude oil is a very large carbon chain. Okay.
Hmm.
So we take a lot of zinc oxides without this so that aromatization is avoided. Okay.
Hmm.
And then we heat it strongly. Then what happens? Usually the crude oil which comes is around C30, 40, 60, these kind of carbon chains you will get. Got
That's
it?
huge.
Yes. Okay. So that is what will you start breaking.
Hmm.
Got it? So this process typically is called breaking of crude oil. Breaking of
Hmm.
crude oil usually is done mostly, in certain North European countries as well as India. Correct?
Yeah.
India usually buys a lot of crude oil and make it and break down into thermal cracking. Got it?
Hmm.
And through thermal cracking, once it is done, then we'll do distillation and
To
separate all the
separate.
products.
Yeah.
And that's what HPCL, BPCL, IOCL, you know,
Hmm.
all of these organizations in our, in India, they all do this. Got it? We are
Yes.
refining companies. You are refining
Hmm.
them. Got it?
Yeah.
So, so we'll refine the crude oil using this process. Got it? That is called thermal cracking. Okay.
Yes, sir.
Next, isomerization. Isomerization is trying to make a straight chain into a branch chain. Okay. So if you
Hmm.
have a straight chain here, you react AlCl3 with some concentrated HCl and heat it. Okay. Then you will be seeing that one of the methyl will break and it will get branched into a new position.
Hmm.
Same way, if you have like this will break and branch into this position or this position. This kind of a branching of a methyl is called isomerization reaction.
Hmm.
Shana, clear beta?
Yes,
That's
sir.
it.
I
Now you see,
understood.
I have rushed out for these reactions because these are not very, very important as such. Yes,
Yeah.
you have to just make it a reading. That's it. Okay.
Okay.
So that ends our reactions of alkanes. Got it?
Yes, sir.
Understood? So the next topic is all about preparation of alkanes, which will continue in the next class. Got it? So you
Yes.
have enough on your table now. So you have to go through these reactions first thoroughly. Got it? Read it
Okay.
again. And most importantly, try to understand whatever the terms we discussed. Okay? Now, my suggestion is
Yes,
simultaneously
sir.
start reading the isomerism notes. So I'm going to upload the isomerism notes also right now. Got it? I'll show you 1 minute.
Okay.
Okay. Now, in the isomerism notes, got it? The
Hmm.
first part is all about structural isomers. Got it?
Hmm.
It will not take much time, but I highly recommend you to do this. Do not do anything about tautomerism here. This you
So
can
I'll
do it
stop before
again.
that.
Hmm?
So I'll stop reading before tautomerism.
Yeah, before tautomerism, that is up to page 8.
Okay.
Up to page 8, you will make a reading first.
Hmm.
I'm pretty sure you'll understand major of the things. Whatever you don't understand, we can discuss in here. Okay.
Okay, sir.
Then you skip out the tautomerism part. Okay.
Hmm.
That goes up to this page number here. Huh. That is up to 20th page.
Hmm.
9 to 20, you skip it out. Then we will start with geometrical isomers. Got it?
Okay.
This is a
Yeah.
complete stereo part. This is
Hmm.
something you need to learn. Got it?
Okay.
Sorry. I have another notes in here. uh, which is a complete notes of it. Yeah, here. Yeah, from geometrical isomers onwards. Okay. So first you go through geometrical isomers. Got it? How to
Yeah.
notate, how to make a notation and all. Got it?
Mm.
This will take up to uh, 11 pages, first 11 pages. Okay. Yes,
Yeah.
there will be a lot of gray areas you may not understand. I want you to mainly focus on the first 3 pages. That is basic understanding of geometrical isomerism. Very basic
Okay.
understanding. First 3 pages is
Yeah.
about basic understanding of geometrical isomerism. That is more than enough for continuing our topics. You don't have to, deal so much. And now don't do confirmations, leave it to me. I'll make you understand confirmations. All of these are
Okay.
confirmations. Correct?
Yes, sir.
After confirmation, this is a part you need to learn thoroughly, which we will be struggling a lot, which is from
Mm.
page number 25. Okay?
Yes, sir.
Shana, clear beta? Right.
Yes, so I'm just writing the names down
Yeah.
so that
Optical
you
isomerism.
can
Mhm.
optical, geometrical, and structural.
Structural.
Okay. Yeah.
So first 8 pages, and then
Mm.
from this document, I'll upload 2 different documents. And in this
Yeah.
document, again, first 3 pages, and after
Mm.
that, from 25th onwards. From this
Okay.
25th onwards, you have to read everything now. Now, this is the most important part.
Mm.
Got it? It
Yes,
will
sir.
have all the questions of his mixed questions, everything. Got it?
Yes, sir.
Okay. Lots of questions I have discussed. These are all various type of questions. So if you could go through it one by one, see these are all. See, can you see the last question also? Number of
Yeah.
isomers, optically active fractions.
Mm.
Next, before that, before that, before that. Like I have taken all possible questions which have been asked in JE so far. Okay,
Okay. Yeah.
correct. First of all, have the spiral notes of these copies first. Okay,
Okay,
do
sir.
not try to depend always on the screen because you have to scribble in there itself whenever it is
Yeah.
needed. Okay, so it's always better to have a hard copy with you. Make a spiral of it, keep a hard copy, and put some empty pages at the end.
Yeah.
Agreed. Before you making it as a spiral, keep some empty
Mm.
pages at the end, so that if you feel like uh, getting back to certain topic or something, you can just write down that page number there itself.
Yeah.
Okay, becomes very convenient and easy. Okay, right.
Yes, sir.
So I suggest you start working on isomerism simultaneously. Okay,
Yes, sir.
every day,
Okay.
even if you do 4 5 pages, that's more than enough. Within 2 3 weeks, you'll cover everything.
Okay. Yeah.
Okay, right.
Yes.
ठीक है बस I'll upload all these three now. I'll be sending you the link for your drive. I'll put all the notes in a drive and send it to you. Okay.
Okay, so I can just print them out at the same time. Like there's no addition or
Huh?
any. I
Yeah,
can print them out all at the same time, right?
yeah. See, this is the drive link I'll be sending you right now. Correct.
Hmm.
So all your notes will be here only. Okay.
Oh, so this is just for me or like all notes that you've made before?
No. Every time we discuss, the notes will get updated. Okay. Like today's
Acha.
session,
Okay. Yeah.
hydrocarbons is there. Now I'll be sending structural and stereo here itself. So you'll notice that. Okay.
Yes, sir. Okay.
ठीक है बेटा. Right.
Yes, sir.
Right. Chalo.
Bye, sir. Thank you,
I'll
sir.
close the session. We'll catch up in the next class then. Chalo. Bye beta.
Yes, sir. Bye, sir.
Bye beta. Good night.